All right, hi guys, this is Dr. Tim Kruse. This is elementary statistics, and in this video I'm going to show you how to find a confidence interval. I'll tell you what it is. Find a confidence interval for population mean, mu, when you know population standard deviation, sigma. When sigma is known, we're going to find critical values. I'll show you how, and we're going to find margin of error. So let me just start with just kind of a general story here. All right, just think about a lake near you, just a big lake. And, maybe you're sitting there on the bank and you're going, I wonder what the average weight of a fish there in that lake is. All right, that number exists. There is an average weight of all those fish in the lake, but we'll never be able to calculate it. All right, it's impossible. We'll never know what the true average weight of all the fish in that lake is because there's just too many of them. We'd have to drain the lake. We'd have to gather millions of fish before they die. We'd have to get a total weight. And then to average it, we'd have to divide by, how many millions of fish there were. All right. So it's just impossible. So, there is a number, but it's kind of an idea. All right. It's not something that we'll ever be able to actually figure out. All right. That's kind of the idea of what mu is. Mu is kind of an idea. All right. It's a true average weight, whatever all of the fish weigh divided by how many fish there are, whatever that average is, it's out there. It exists, but we just aren't able to calculate it. And we call that number that's kind of an imaginary number, we call that mu. All right. That's the population mean. Mean means average, sometimes called the true average. All right. So the true average is out there. We're not able to calculate it. So what we do instead is we just take a guess at it. All right. We're never going to know what the true average weight of the fish in the lake are, but we can take a guess at it by taking a bunch of samples. And these samples we call X bar. So maybe I'll go to, the north end of the lake and I'll catch a couple hundred fish. And maybe I'll go to the south end of the lake and catch a couple hundred fish. And then the west and then the east, and I take these 4 or 5 or however many samples and I average each one of their weights. I average the weight of the north fish, I average the weight of the south fish, and so on and so on. And by taking a bunch of samples and looking at their averages, I can kind of guess at what the true average weight is. I can kind of guess at mu. So X bar is something that we actually can measure. All right, this is kind of the fish we can catch. So all the fish that we can actually catch and measure, we're going to take a bunch of those samples and we're going to look at those and kind of guess at what mu is, that true average weight of the fish in the lake. All right. So maybe after taking many samples, I go to different parts of the lake, I catch a bunch of fish, I average all those weights and I take a look at them. Maybe I'm pretty sure that the true average weight is between 1 and 3 pounds. After I take all of my samples, after I do all of those X bar calculations, maybe I'm pretty sure that I could say, I could put it on a sign outside the lake or something. And I could say, hey, if you go fishing here, the average fish will weigh between 1 and 3 pounds. That's something we can say. All right. Or I can say it like this. I can say something like, we are 95% confident. So you got to be pretty confident before you put it on a, billboard outside the lake. We are 95% confident that mu, the true average weight, lies in the interval from 1 to 3 pounds. All right. That's a confidence interval from a low weight of 1 pound to a high weight of 3 pounds. We're pretty sure that if you just grab a fish out of the lake at random, it'll weigh on average between 1 and 3 pounds. All right. Looks like mu, the true average weight, is kind of in between there. So halfway between 1 and 3 is 2. So it looks like we're guessing that mu, the true average weight, is probably 2 pounds, just halfway between 1 and 3. So we're guessing that mu is probably 2 pounds, and we're going to give ourselves a little bit of insurance, a little margin of error is what we call it. So 2 pounds minus a pound makes it 1 pound for a lower limit, and 2 pounds plus a pound makes it 3 pounds for an upper limit. So we say my confidence interval is from 1 to 3. This is the lower limit, like a boundary. And this is the upper limit. That's like an upper boundary. And somewhere in between there lies mu. We're kind of guessing that it's 2. All right. So our confidence interval would look something like this. We would say mu that true average weight of the fish in the lake, which we're not actually able to calculate, that we're kind of guessing at, we say mu is between 2, all right? That's kind of our X-bar average, and then minus a little bit of insurance and plus a little bit of insurance. It's kind of like saying mu is 2 pounds, give or take 1 pound. This would be give a pound. This would be take a pound. So add a pound on, take a pound away. That's what give or take means. So we're saying mu is 2 pounds, give or take a pound. And how did we get that? Mu is between all those sample weights we took, X bar, all right? All those sample weights we took, plus a little bit of error and minus a little bit of error. That gives us a little bit of a spread because we don't know exactly what mu is, but we can kind of guess at it with our X bars. We can look at our X bars and kind of guess what mu is, and we just need to give ourselves a little range, a little insurance, a little give or take. All right, that E right there, that 1 pound give or take that we did, that's called E for error, specifically called margin of error. So our margin of error is plus or minus 1. We think the average weight is 2 pounds, but give or take 1 pound, plus or minus a margin of error. All right, let me give you a more specific example, but let's kind of review our normal distribution curve first. Remember, zero's in the middle, that's mu. All right, it splits the curve in half, so I have 50% to the left and 50% to the right. I like to think about it as there's 100 people under the curve. Most of them are in here, but there's 100 people under the curve. They're all under the curve somewhere. So if you add up all these numbers from the left side to the right side, that's going to add up to 100%, or sometimes I say 100 people. So there's 100 people under the curve. Now, most of them are in the middle here. See, there's 34% here. That's like 34 people out of 100. And there's 34 people here. So from one step left of the true average and one step right of the true average, that's kind of what we were talking about. My, average weight is 2 pounds plus or minus a pound. That's kind of the same idea. This is mu right here in the middle. This is the true population mean, the true population average. And then if I take one step right and one step left, well, 68 out of those 100 people, that's what this 68 means, from here to here, 68 out of those 100 people live right in there. These are kind of all the really, really normal people. A little below average, a little above average, but all 68 of these people are pretty darn close to being average. If you're within one step, you're just pretty darn average. Now, if I take another step, if I go 2 steps to the right and 2 steps to the left, well, there's another 13.5 people living out here, 13.5%, and there's another 13.5% living out here. So if I add those guys all up, well, now I'm up to 95% from here to here, from 2 steps left of mu to 2 steps right of mu. All right. So if I go 2 steps, I'm encompassing 95 people out of 100. That's 95% of those 100 people. That's most of them. All right. And I could go further, but that's just kind of an estimate. There's about 34 people here. There's about 34 people here. There's about 13.5 people here. There's about 2 people here. And there's just a part of a person out here on the end, all right? But if you go through and add all these up, they should add up nicely to 100%. Remember, these are just approximations. They're not exact. It's just some numbers just to kind of get an idea of what we're talking about. All right, so let me give you another example here. You guys have all sat at home waiting for, the cable guy or whoever, your Amazon package, and they tell you a certain time to expect it. Like they might say, hey, the cable guy will be there to install your thing at noon. All right. Now we kind of know that's a lie. All right. They never show up on time. Something always happens. But what they're going to say is noon. All right. Noon is mu. Noon is their advertised claim, or sometimes we call it expected value. It's what time we expect him to be there. It's what time they advertised that he would be there. We usually call it population mean or true average. These are all different names for mu, the middle number. So I wrote in 12 o'clock right there under mu. All right, 0 is mu. So we expect him to arrive at 12, but he probably won't. All right, they should have said, well, he'll arrive at 12, give or take an hour. That would have been more honest. So they could have said something instead like this. We're 68% confident that he'll arrive at noon, give or take an hour, plus or minus 1 hour. All right, so a 68% confidence interval would be from 11 to 1. If you look up here, all right, here's 12 o'clock, 1 o'clock, 2 o'clock, 3 o'clock, 11, 10, 9, all right? They said he'd arrive at noon, but he probably won't. But if they say, well, he could arrive from 11 to 1, we're 68% confident that he'll arrive between 11 and 1. That's a confidence interval. How confident are they? They're 68% confident that his true arrival time, mu, will be between 11 and 1. They're 68% confident that his true arrival time, he might arrive at 11:55 or 12:34, but they're 68% confident that his true arrival time will land somewhere in between 11 and 1. That's what a confidence interval is. All right. Now they could write it like this. So a 68% confidence interval would be 11 to 1. And here's how we're going to kind of start writing it, using statistics speak. We're speaking statistics. We're going to say mu is between, could be 12 o'clock minus an hour, could be 12 o'clock plus an hour. That's 12 o'clock give or take an hour. All right. Here's the stat way of writing it. We're saying mu is between, our estimate, x bar, that's their estimate, minus a margin of error and plus a margin of error. This is his true arrival time. We expect that he will arrive between, our estimate of 12 o'clock plus or minus a little bit of error. All right, that's kind of insurance. If I wanted to say, well, I need to be more confident, maybe I want a 95% confidence interval. Well, a 95% confidence interval would be the 13.5 and the 34 plus the 34 plus the 13.5. That adds up to 95% from 2 steps left to 2 steps right of mu. All right, so from here to here makes me 95% confident. So if they ask for a 95% confidence interval, I need to tell them, that interval will be from 10 o'clock to 2 o'clock. All right. If I say, I think he'll arrive at noon, that's X bar, kind of what you think, not the true arrival time, but what you think. I think he'll arrive at noon, give or take 2 hours. That interval would be from 10 o'clock to 2 o'clock. So now they can say with 95% confidence, the guy will be there to install your cable between 10 and 2. All right. They can be 95% sure if they say it like that. All right, let's kind of do an actual problem here. So maybe you're wondering what the average weight of a hummingbird is. All right. I don't know what the true average weight of a hummingbird is, because to find that, I would have to catch all of the hummingbirds in the world and weigh them. And then to find an average, I would have to divide that weight, that total weight, by how many millions of hummingbirds I caught. So they're talking about mu right there. The average weight of a hummingbird, that's mu. The true average weight, we'll never ever know. We can't catch all the hummingbirds and weigh them and average it. All right, it's impossible. But we can guess at mu by, catching the ones that we can catch. As many as we can catch, we'll kind of weigh them and make an average weight for them. And then we'll kind of guess at what mu might be. So given you were able to catch a sample, that's going to be our X bar, all right? We were able to catch 14 hummingbirds. 14 is N, by the way. N is number, the number of samples you took, number of birds we caught. So, and the average weight of your sample is 3.15 grams, okay? X bar means average, just like mu means average. So mu is like that mythical average weight, the true average weight of hummingbirds, the thing that we'll never be able to calculate because there's just too many. But X bar means the same thing, but it's for your sample of the 14 that you actually caught. This is real. I can actually calculate this, all right? I'm going to weigh those 14 hummingbirds. I'm going to get a total weight, and I'm going to divide it by 14, and that average is 3.15. So X bar, your sample, can actually be calculated. Mu can't be calculated. It can only be guessed at using X bar. All right, so you were able to catch 14 hummingbirds, and your average weight was 3.15 grams. That's X bar. And in this case, sigma, the population give or take, the population standard deviation, is known to be 0.38 grams. So they're giving you that. They're just saying, we know, based on observation, that the population, give or take, the population standard deviation is 0.38. Now, if you know sigma, we're going to use the z-table. That's just something you're going to have to remember. If you know sigma, you use the z-table. If you don't know sigma, you're going to use the t-table. And that's another lesson. All right, so we know the population, give or take, the population standard deviation. We know we're going to use the z-table. And now they ask us to find an 80% confidence interval for the true average weight. That's mu. All right, we're kind of guessing at mu for the true average weight of a hummingbird. Okay, first step is get organized. So this is how I do it, but you can do it any way you want to. I start with how many hummingbirds was I able to catch? So my number was 14. All right, what's the population average weight? Nobody knows. All right, we're not able to calculate that. You can't catch every hummingbird and weigh them and divide by 5 million hummingbirds or however many there are. Population standard deviation was given 0.38. So these are your population numbers. That's population average, population mean, and that's standard deviation for the population. These are the same numbers for your sample. This is your sample average or your sample mean, which we figured out was 3.15 grams. All right, we caught 14 hummingbirds, added up their weight, divided by 14. On average, our sample weighed 3.15 grams. And then S stands for your sample standard deviation, which we don't know, but which is not necessary for this problem, for this confidence interval. So we're going to use our sample to guess at mu. And in this case, we know the population standard deviation, all right, which tells us to use our z-table. Now, the next thing we write down is, what confidence level are we trying to do? Is it 80%, 90%, 95%? What is it? So we write down, okay, they asked us for a confidence level, a C of 80%. And then the last thing that we have to figure out is we have to find the Z number for that C number. I need to find the Z number that matches up to that C, all right? If I want an 80% confidence level, I need to know what Z numbers are we talking about. Are we talking about from one step left to one step right, or 2 steps left to 2 steps right? I need to know exactly what that Z number is. So I write down, I want the Z of that confidence level. Well, this confidence level is 80%, so I want the Z that's associated with 0.80, all right? I want the Z number that encloses an area of 80%. Now that's 1.28. I'll show you how to get it here. All right, here's a picture of what we're talking about, all right? Here's our normal distribution curve. Mu is in the middle, all right? And there's 1 step to the right, 2 steps to the right, 3 steps to the right. Here's mu, 1 step left, 2 steps left, 3 steps left, all right? They asked us to enclose 80%. They want a confidence interval from here to here, and they want 80 out of 100 people to be in between those two boundaries. All right, so think about it. If 80% is in the middle, that means 10% is over here and 10% is over here. If 80% in the middle, that's 20% left over. Split it exactly in half because we're sitting in the middle. Split that 20% exactly in half. That means 10% is here and 10% is there. All right, now what do we look up? All right, guys, remember, I can't look up the 80% in the z-table. I can only look up areas to the left, all right? So what I'm going to look up is I'm going to look up this 10%. I'm going to go grab my z-table, and I'm going to find out what z number, pretend you don't see that number there, I'm going to find out what z number has an area of 10% to the left of it. So let me grab my z-table here. All right, so I've got my z-table. Now, first of all, I noticed that here's mu, that's 0. This is -1, -2, -3. All of these z's over here are negative. So I'm on the negative side of the curve. I'm looking for a negative z. So I grab my negative z. All right, I grab my negative z table, and I look in here for an area of 10%. Now 10% is 0.10. All right, 0.10. Well, I got a lot of 0.10s, but remember, 10% is 0.10, and then just add a couple more zeros, 0, 0. So 10% is 0.1000. And I'm looking through here, and I want to get, you hardly ever land right on it. But gosh, that's really, really close right there. 0.100, that's almost 0. That's close enough, all right? So this is an area of 10%. Now what z produced that? -1.2, and then I go up to the top, 8. negative 1.28. So that's where I came up with this z right here. I tried to figure out what z number produced an area of 0.1000. And I got as close as I could, and I said, okay, it looks like negative 1.28. So I kind of placed that on the curve appropriately. I went about 1 1/4 of a step to the left. That's about 1 1/4 step to the left. Now its twin, its positive twin, is going to be over here. Remember, this is sitting right in the middle. So whatever this number is, this will be the same number, only positive. So I did 1 1/4 step to the left, and I did 1 1/4 step to the right. All right, I shade in the middle. That's 80%. Now what do I need to do? I need to change these z numbers to my story problem numbers, my hummingbird weight numbers. But before I get to that, I want to show you that you don't always have to do all of this work. If you have the table that I'm looking at here, this number right here is in your table. Now remember what you're looking for. You're looking for an 80% confidence interval. And on my table, if you go to the positive side, I'm on the wrong side. If you go to the positive side, down at the very bottom, they've actually already got your confidence intervals figured out for you. We were looking for an 80% or a 0.80 confidence interval. Well, that is both of the 1.28s. That's the negative 1.28 to the positive 1.28. That's what we just figured out the hard way. But if you have this z table that I'm looking at here, usually at the bottom they'll have this all figured out for you. A 90% confidence interval would be from negative 1.645 all the way to positive 1.645. Most of the time they use a 95% confidence interval, which would be both of the 1.96s. It'll be from negative 1.96 all the way to positive 1.96. So that's kind of handy if you have that on your z table. Oops, sorry. All right, so back to our problem. We know that mu, that true population average weight of a hummingbird, is between the 1.28s. All right. Now I'm speaking z there. Your z numbers are your 0, 1, 2, 3 numbers. This is 0, 1, 2, 3. This is 0, negative 1, negative 2, negative 3. All right. I call your z numbers your 0, 1, 2, 3 numbers. So we're speaking in z. All right. We got to change our z language to an x language. Now x is just the language of your problem up above. Your problem up above was speaking in, weights of hummingbirds. So I have to change these z numbers, these 1.28 numbers. I need to change them to story problem numbers. I need to change them to my word problem numbers, which we call x. So these are z numbers, and then our x numbers will be our hummingbird weights. So given that mu is between 1.28 to negative 1.28, if you're speaking z, the question is, well, what is mu between, if I change languages and I speak x? Hummingbird weight to hummingbird weight. So I got to change the 1.28s to a hummingbird weight, and that'll be my confidence interval. All right, here's how we start out. So we say mu is between our sample average weight minus a little bit and plus a little bit. That's our give or take. So it's our sample. Where'd my other finger go? There we go. It's our sample weight, give or take a little bit of error. Give or take a margin of error. Now we have a nice little formula for this. Our margin of error, that's just the z number that we just figured out. All right, the z number for this particular confidence level, it's going to be 1.28. We're going to use the positive number, times your population standard deviation, if you know it. We do. Now we have to adjust the standard deviation for our small sample size. So dividing by square root of n, that's just an adjustment. We have to adjust the standard deviation. So we divide by a square root of how many birds we were able to catch. All right, and then we do the same thing over here, but with plus. So let's plug in some numbers. The rest of it's pretty easy. So over here, x bar, the average weight of our sample was 3.15 grams, minus, what's the z number we were talking about? 1.28, times the population standard deviation that was given, 0.38, which we have to adjust by dividing by square root of n. We caught 14 hummingbirds. Same thing over here. The only difference is plus. So I know that mu is between whatever these work out to be, and that'll be our x number. All right. Let me go ahead and show you the answer, and then I'll show you how I got there. All right, let's grab the calculator here. And I got 3.15 minus 1.28 times 0.38 divided by square root 14. How's that look? I think that's right. And there's my 3.02. All right. Now, you guys on TI 83s and 84s, and most of the scientific calculators will do this as well. I don't want to type that whole thing in over again, so I'm just going to arrow up, hit enter, and it brings it back up. And your scientific calculators will do roughly the same thing. You might have to do it a little differently, but you can bring up your last entry. And all I'm going to do is just change that minus to a plus and hit enter. And there's my 3.28 over there. So you don't have to type the whole thing in over again. All right. So what are we saying? We're saying based on my sample, the 14 hummingbirds I could catch, I am 80% confident that the true average weight, mu, whatever that number is that we'll never be able to calculate, I'm 80% confident that the true average weight of a hummingbird is between 3.02 and 3.28 grams. Okay? One more time real quick. Figure out what Z numbers you're talking about and change them to X numbers, just using your formula. Okay, a couple other questions you might be asked is they might ask you, what exactly is your margin of error? What is that give or take that you're adding or subtracting? Well, your margin of error is just this calculation right here. This 1.28 times the 0.38 divided by the square root of 14. That's your margin of error, all right? So all you got to do is do that calculation separately, all right? Don't involve the 3.15. Don't worry about the minus. Just multiply and divide, all right? And my margin of error is 0.13. So up here we're saying, based on my sample weight of 3.15, I think that mu is 3.15. I think the true average weight of a hummingbird is 3.15 grams plus 0.13 grams or minus 0.13 grams. That's my margin of error. So if they ask you what the margin of error is, just calculate this part separately. That's your give or take. You're saying, I think it's 3.15, give or take 0.13. All right. Another question you might be asked is, what sample size do you need? All right. What sample size is needed? Now, what they're really saying is, well, how many birds would you have to catch? And they're asking, what would N need to be? Sample size is N. So if they say, what sample size is needed, or how many birds would you need to catch? If the maximum error could only be 0.14, instead of what we got a margin of error of 0.13. So if they're saying, hey, I can't have this margin of error, I need this margin of error instead. Well, that changes how many birds you need to catch. So how do you calculate that? Well, there's kind of a hard way. Just use your margin of error. All right, your margin of error is this calculation right here. So you can put in the numbers that you know. All right, I want to change error from 0.13 like it was. I want to change it to 0.14 because that's what they're saying. What if I don't like, a margin of error of 0.3? What if I want the margin of error to be 0.14? How many birds would I need to catch to change that? Well, if I want to change error to 0.14 and then I plug in the Z and this sigma that I know, I'm left with this equation right here, which is kind of tricky to solve using algebra. If you like algebra, you can go ahead and solve this and figure out what N is, but it's actually easier if you just rearrange this formula first and get the N alone. And I've done that for you over here. So this equation and this equation are the exact same thing. It's just over here the margin of error is all by itself. It's isolated. And over here the N is all by itself. It's isolated. All right. Through the magic of algebra, we've gotten the N alone. So this is the same equation. This is easier to use. How about we just use this one instead? So what would the number need to be? Well, my Z number is 1.28, my sigma is 0.38, and they said change the margin of error to 0.14. Well, just plug that in your calculator, and you get the number of birds that you need to catch is 12.07. Now remember, you can't have part of a bird. We're talking about birds here. You got to relate it to the problem. So I'm going to have to round that up to 13 birds. You can't have 12 and part of a bird. You can't catch 12.07 birds. So I'm going to have to catch 13 birds. So just always round up on your, your sample size. Okay, last page, and I just have one for you to try here. So pause the video here in a minute, copy this down, and go ahead and work it out just like we did the last one. So find a 95% confidence interval. So you have a different confidence interval. Given you, let's just make up your own story. Given you caught 14 fish, n equals 14, and the population standard deviation is known to be 1.95. Now those 14 fish you caught, they averaged 5.35 pounds. All right, and you're wondering what mu is. You're wondering what the true average weight of a fish in that pond is. If your sample is 5.35, you're trying to guess at what the true population average would be. You're trying to guess at what mu would be. And then also answer your margin of error and what sample size was needed if I wanted to change your margin of error to 1.20 instead of what you get with this problem here. So pause the video, take a shot at it. All right, hopefully you paused the video. Here's a little hint about how to organize and draw your curve. All right, so how many fish did we catch? 14. What's my population data? Well, the true average weight is unknown. They told us that sigma, the population standard deviation, is 1.95. So those are the two population numbers. Here's the two sample numbers. All right, the fish that I caught, their average weight was 5.35. My sample average, my sample mean. And my sample standard deviation is unknown, but we don't really need it for this problem. What's your confidence level? They said I need a 95% confidence interval. And what's the z number associated with that 95% confidence level? Well, that's going to be 1.96. All right. You can figure it out the hard way. Now, the hard way is 95% leaves 5%. Split that 5% in half. That leaves 2.5% here and 2.5% here. So you can look up 2.5% in the negative z table, and you'll find that negative 2.5% is a z number of negative 1.96. Or if you have that handy little table like I did in the bottom of your z table, you can just look up 95% confidence interval and it'll tell you both of the 196s. So from almost 2 steps left to almost 2 steps right, that encompasses 95 out of 100 people, or 95% of the curve. So we know that the true average weight of the fish in this pond is somewhere between negative 1.96 and 1.96, but that's the wrong language. We're speaking z there. I want to relate it to this problem up here, so I need to change my z numbers back into x numbers. So if I'm speaking x, I'm asking the true average weight of a fish is between, and I want to know how many pounds on the lower limit and how many pounds on the upper limit. Grab your formula. All right, it's basically your sample plus a little bit of error and your sample minus a little bit of error. So the true average weight of a fish in this pond is my sample give or take some error. So the true average weight of the fish in the pond is this formula, same formula. This one's plus, this one's minus. The rest of it's just plug in your numbers. So the fish that I caught, their average weight was 5.35. My sample average, my sample mean, minus the z number for this 95% confidence interval. That's negative 1.96. Don't worry about the negative. The minus takes care of it. Times 1.95 was given as the population standard deviation. And then we adjust the population standard deviation for a small sample size by taking it divided by the square root of n, the 14 fish we caught. Same thing over here, but plus gives you a true average weight somewhere between a lower limit of 4.33 pounds and an upper limit of 6.37 pounds. So here's the start of the problem. Mu is somewhere between the 196s if we're speaking z. Mu is somewhere between 4.33 pounds and 6.37 pounds if we're speaking x, if we're speaking in the story problem numbers. To finish out the problem, you're saying I am 95% confident, it's a 95% confidence interval, that the true average, mu, is somewhere between 4.33 pounds and 6.37 pounds. All right. If you're that confident, you can like post a sign outside the pond that says, hey, if you fish here, on average, you'll catch a fish between 4.33 pounds and 6.37 pounds. All right. Because I'm 95% confident that will happen. So now you can advertise that claim. If I ask you what the margin of error is, that's E. That's just this number right here, the thing that you're subtracting or adding to your sample. All right, that little bit of insurance you give yourself. Plug in the numbers. So we're saying give or take 1.02. So we're saying mu, I think mu is 5.35. We're saying it here and here. I think mu is 5.35, but I want to give myself a little give or take. All right, I want to do plus 1.02 minus 1.02. So I think it's 5.35, give or take 1.02 pounds. All right, and then finally, what if I wanted to change that margin of error from 1.02? That's what we currently have. Our margin of error is 1.02. Our give or take is 1.02 pounds. What if I want to change that to 1.20? Well, use your rearranged formula, plug in your numbers, change your E, not from 1.02. Don't use 1.02. Use the new margin of error, 1.20. And that says, well, you would have to catch 10.14 fish. You can't catch part of a fish. You got to round that up. You would have to catch 11 fish. If your sample was the size of 11, if you caught 11 fish, your margin of error would be 1.20. If you catch 14 fish, your margin of error is 1.02. All right, guys, that's it.